Hello, folks. This is lecture 10 of the Mechanical Vibrations course. And on the agenda, we have simply discussing the rotating unbalanced problem. Now, the last 10 minutes of the lecture on Tuesday, I briefly introduced you the concept and I quickly derived the equation of motion for such a problem. However, I would like to go through it one more time and do a quick review of what transpired. So we have a machine, this rectangular box that you see here, you can view it as a machine. Inside of it, there is a rotating component. That rotating component can be a turbine, can be a blade, a fan blade, a fan, but anyway, something that turns about this location, this axis of location. Now, the machine itself has the big rectangular piece is mass of m, and inside of it, there is that rotating component with the mass m naught. Now, the machine is supported by a foundation, which we are representing it by, for example, the spring and a damper. And rotating unbalance is a very common cause of vibration in everyday life. So, for example, this rotating component, its mass center may not be at the center of rotation. That being the case, essentially we can treat it as a mass at the distance, which is the distance between the mass center and the axis of rotation, which is denoted by little e, the eccentricity. So we can view this whole shebang as a mass of m naught rotating about this point, with maybe connected with the massless rigid bar. Okay, so this is a simplified version. Now we don't draw the turbine or the fan structure. What we do is we designate the mass center of that thing that has an unbalance, perhaps due to a chipped, chipped piece, or maybe there's a extra mass attached to one of the blades, etc. The moral of the story is that the mass of the rotating component, we can view it as m naught, and it's located at the mass center, which is a distance e away from the center of rotation. Now, let's say that this rotates at a constant speed omega r, and r represents the rotation, omega r. So the angle that you see here, we can think about it as omega r times t. Obviously, this omega r is radians per second multiplied by seconds or t, you're going to get the angle. Okay? Now, once again, the rotating unbalance, that mass is called m naught, distance e, and the combination, it's a common term in rotating unbalanced literature, that the product of m naught times e times the gravity constant is called unbalance. So if you're ever asked what is the unbalance in this machine, you need to know the mass of the rotating component, you need to know the eccentricity and the gravity constant, and this combination will give you the unbalance of the machine. Now what you want to do is to get the equation of motion governing this problem. First of all, notice that we are assuming that this machine is made of, as I said, rotating unbalance. And if we isolate the rotating component on the side, so I've taken the rotating component out of the big box here, big block. So whatever is left of the big block is m minus m naught, because the rotating unbalance has been taken out and isolated here. And this machine can go only up and down. It's supported on the side, so it it cannot go sideways, and we're only interested in the up and down motion of the machine. Therefore, when you take the rotating component out, that is the thing that was actually making this block go up and down. And because it's an internal force, when you look at the rotating component itself, there is the equal and opposite value for FR, which is acting on the rotating component. Therefore, the free body diagram of the mass, the rotating component, is drawn FR here, and that's pretty much it. There's nothing else, okay? There is no other external force that's acting on this. Now remember, we are assuming that things start at the equilibrium position or measured at the equilibrium configuration, therefore we don't have to worry about gravity, okay? Now, the motion of this mass, of course, it goes up and down. This mass M0 goes up and down because it travels with the block here, which can only go up and down, but it's also rotating. Therefore, we can say that the vertical distance, of the mass M0 from the horizontal axis is eccentricity times the sine of that angle in this right triangle, hypotenuse times the sine of that angle, but sine of that angle, we agreed that it was omega RT. So therefore, the vertical position of the mass M0 in not only x, which is coming from the big box, because it travels with it, plus the thing that you just got. Now, if this is the vertical position of the mass, just the vertical position of the mass, not counting the traveling with the block itself, the acceleration, vertical acceleration of this mass is simply differentiate this thing twice, and you're going to get minus e omega r squared times sine. Okay, now we're going to draw the free body diagram of the isolated rotating component and the big box, which is the machine minus the isolated or the rotating component. Okay, so let's start with the free body diagram of the rotating mass. The only force that's acting on it is Fr, and it's downward because you're assuming that positive is up. And it's got a mass of m0 based on Newton's law. This is equal to this force is equal to mass times acceleration. The mass is m0 because we're only looking at the rotating component, and the acceleration, we just discussed it, is going to be acceleration due to the block and the acceleration due to rotation, so it's the sum of these two. Okay. Now, when you look at the block itself, well, of course, Fr is pointing up. There is the damping force, Cx dot. There is the spring force, Kx. And the mass of this block is the big M minus m0 that was taken out. So there we are. This is the Newton's law for the machine itself. Now, if you add these two up, notice that several things cancel out. For example, m0 x double dot is here, and m0 x double dot is there. They cancel out. One is positive, the other one is negative. Fr, one is positive, the other one is negative. So essentially, we get a very simple expression, and once you take everything to the left-hand side, this is going to be your equation, okay? So I added these up and took everything to the right-hand side, and this is what I get. However, we know what x double dot, xr double dot is. We know that because it's right here. You just plug it in, and there's nothing unknown about it. You take it to the right-hand side, and you get the mother of all equations for a rotating unbalanced problem, rotating component. So you're familiar with the left-hand side, and the right-hand side, you have seen it, because we spent about almost a week and a half on looking at the situation where a mass and a spring and a damper was subjected to harmonic load. And this is a harmonic load. It's just that we called it, when we treated this, the right-hand side, I called it F naught, big F naught, times cosine of omega t. Okay? All right. My big F naught is this thing, m naught e omega r squared. And instead of cosine, I have sine. It makes absolutely no difference. We know what the solution to this equation is. We spent a whole week on doing this thing. So let's go there. And let me write the equations here for. So first of all, we know what the solution to that equation is right here, right there. This middle xp of t is the solution to that equation, except that where it's coming from is that from last week, we had cosine on the right-hand side, so now we have sine, no problem. And there is an amplitude, big X, and there is a phase, theta, okay? And these things, we discussed what the theta is and how to calculate X. We did that last week. But again, it's going to come in these transparencies, but let me not worry about that right now. Now, we also found the transmitted force to the ground. This we did it on Tuesday. Okay, we did the transmitted force to the ground as being F naught. There is my F naught times R squared. Remember there was an R squared there, times this shebang, which is what we did last week, on Tuesday, actually. Okay. Now, in here, this alpha, if you're talking about the transmitted force to the base, to the foundation, to the ground, this alpha is given by that expression. And just keep in mind that M is the total mass of the machine, and M naught is the mass of the rotating component. Just remember that. Now, I said that we did this thing last week, and there we are. The big X came out to be F naught over K. Let me remind you that. Big X came out to be F naught over K. And if you write your value of F naught, which is this combination without the R squared, and you write the value of K, and you clean it up, you're going to come up with this expression. There is your amplitude of the oscillation of the block, which means the machine. There is the phase of the block, okay? And R, of course, is the frequency ratio. Nothing new. We spent the whole week getting to this point, okay? We're just using it. Identifying what F naught is. Big F naught is M naught E omega n squared. All right? And using the same formulas, except that instead of big F naught, which I just told you, just simplify and you get this. All right. Now, this transmitted force right there can also be, if I divide both sides by M naught E omega n squared, and that is nothing new. Last Tuesday, we did Ft of time equal to, there was an F naught here, and there was an R squared. So I'm taking the F naught to the left-hand side. That's what we did on Tuesday. So there is the expression, non-dimensional expression for the transmitted force. Okay? This all looks familiar to you from Tuesday. All right. And keep in mind that this combination, we called it M naught EG, is called unbalanced. Okay, that's just the terminology. Now, a couple of observations here. First of all, when zeta is bigger than 1, when the damping ratio is bigger than 1, in other words, you're looking at these curves, 1, 1.5, 2, etc. The deflection, the maximum deflection, this deflection ratio is less than 1. You can see that. It's an observation that you can see. So an increase in the amplification of the amplitude caused by an unbalance can be eliminated by increasing damping. Another way is this. You don't like how far your mass or machine is vibrating as far as the amplitude is concerned? Just use a bigger damper. Okay. Make it as big as you want until you're happy with the oscillation of the block, the rectangular block. The problem is that there may be some limitations. I mean, it may not be practical to bring down the vibration of that block into the level that you may like. It's just that there may not be practical. Okay, now, if the machine, the rotating component, is turning very, very fast, okay, look at the effect of this unbalance. It cannot do much harm, okay? You may not like the level at which it vibrates, but essentially it says that the effect of unbalance is limited because it all goes to 1. This ratio goes to 1. The effect of unbalance is limited for high speeds. And this is irrespective of the level of damping. Irrespective of the level of damping. And that's what's saying. It's that damping is not important when the speed is very high. Okay, now, this model can be used for essentially replicating the situation in a car, for example, in an automobile, when, for example, there is out of balance wheels, etc. So the value the omega r is determined by the speed of the car. Remember, omega r is how fast the wheel is turning in radians per second. Okay, and if there is an unbalance, that unbalance is kind of at the distance distance e from the center of rotation. That's what we call eccentricity. And the passenger or the driver can feel this rotating unbalance. The fact that the wheel is unbalanced by the shaking of the steering mechanism. Or the shaking of the steering wheel. You can see that, for example, the wheel is really, really shaking in your hand. Okay. Okay. And for the situation when r is equal to 1, close to 1, at least you can look at it. R equal to close to 1, we can see the magnitude of the oscillation is high. Once the driver increases or decreases the speed, that shaking goes away. Okay, but essentially we are getting away from the resonance effect. Okay, at r equal to 1, you can view it as having resonance, but with increasing speed, you're going away from the resonance. This level of the amplitude of the vibration of the block, or that block, meaning the thing that goes up and down, is reduced. Okay. Okay, so this is going to be our first example, and it says that we have a machine, rotating machine, that the maximum deflection at resonance is found to be 0.1 meter. So when the value of R is equal to 1, that means at resonance, the deflection, big X, is equal to 0.1. That's what the first line says. Now, based on logarithmic decrement based on the measured data. Remember, you can estimate the damping ratio, and it says suppose that we did that and came up with 0.05. Okay, and we know that the out of balance mass is 10% of the whole mass, and all that means is that little m naught is equal to 10% of m. Okay, just remember, little m naught is 0.1 times m. That's what this line says. Okay, now, what we want to know based on these comments, we want to know what is the value of E. Okay, and then once you get the value of E, it says, okay, how much we have to increase the mass of the machine, okay? The mass of that block, how much we have to increase the mass of the block, how much we have to add to M so that the amplitude of the vibration at resonance, instead of being 0.1, becomes 0.01 meter. Okay, let's not worry about this right now. We go to the part A. So we know something about big X. Write the expression for big X. There we are. Now at resonance, R is equal to 1 in this expression. Simplify, set R equal to 1, and you get 1 over 2 zeta. You can see that. When R is equal to 1, this is 0. This is 2 zeta, square root, and it's going to be this. So what do we know here? This ratio is 10. Remember I said M naught is 0.1 M. So that means this. We know value of X. You're told that it's 0.1 meter. Which is 10 centimeters basically. We know the value of zeta. Based on experimental data, zeta was found to be 0.05. The only unknown here is this little e, which is right there. In other words, the machine has a rotating component whose mass center is 10 centimeters away from the axis of rotation. That's part A. Now part B says, okay, again at resonance, so we have this condition. This is the condition at resonance. Remember, generally it's like that. At resonance, R equal to 1, it's reduced to this. It says how much we have to add to M. By how much we have to add to M? Delta M. So that X becomes, instead of 0.1, becomes 0.01. So M plus delta M, our job is to find delta M so that X becomes 0.01. Everything else we know from before. Solve for delta M. If you solve for delta M, you will see that it's going to be 9 times M. Incidentally, let me remind you that this M naught, we were told in part A, statement of the problem, that M naught is 10% of M. In other words, this M naught was 0.1 M. 0.1 M. Okay. You just plug it in. There's your 0.1 M that I said. Plug it in and find the value of M naught, delta M. Find the value of delta M in terms of M. It's going to be 9M. In other words, whatever the mass of the machine is, make it 9 times bigger. So the mass of the machine, the total mass, must be increased by a factor of 9 so that your level of vibration of the machine, that block, rectangular block, comes to 1 centimeter from 10 centimeters. I mean, that may not be possible, but anyway, that's a theoretical solution. Okay, this is going to be our second problem. So rotating unbalance is of utmost importance in rotorcrafts, such as helicopters and prop planes. So as long as you have a propeller, basically, you may have an issue with rotating unbalance. So here's what we know. Suppose we take the tail of a or the rear propeller of a helicopter, okay? And let's say that the mass of that propeller is 20 kilogram and is turning at a constant speed, of course. And there is a little thing that is a little mass that is stuck to one of the blades, half a kilogram. Now, there's some information given here. For example, it says, let's say that the mass of the tail section is 60 kilogram, and the stiffness of the the tail section is 100,000 Newton per meter. Now, remember, essentially, when you think about this thing, we can, as a very crude approximation, the tail section, we can view that it's a cantilever beam clamped at the left side and, acting as a fancy spring on the right side. All right. Now, we know that the location where this mass is stuck to the blade, half a kilogram, 500 grams, is 15 centimeters away from the center of rotation. Okay. Now, let's say that we have a damping ratio of 0.01. Remember, damping ratio is something that can be found experimentally, maybe by recording some data and using the logarithmic decrement to estimate the value of zero. We have done that. So somebody has done it and said that, okay, in this single degree of freedom system approximation of a very complicated problem, your damping ratio is 0.01. And we know that the tail rotor propeller is turning at 1500 RPM. What we like to know is what is the deflection of the tail section, okay? Amplitude of deflection of the tail section. And then once we do that, the second part, it says, okay, suppose you have, what is the maximum? At this 1500, fine, we calculated the deflection, but the question is, what is the maximum deflection? In other words, another way of saying that is at the resonance, where R is equal to 1, what is the amplitude of the oscillation of the tail section? Okay. Now, one thing is, hopefully, we can see that this tail section is kind of heavy, 60 kilograms. So we cannot ignore the mass of this spring. This tail section is acting as a spring. We cannot ignore its mass, and we know that based on the stuff that we did about 10 days ago, how to account for the 60 kilogram mass of the spring. We take a third of it and add it to the mass that is being modeled oscillating up and down. Okay, there we are. So the natural frequency is going to be the stiffness. We know the stiffness is given here. And let me again remind you that these can be estimated based on the cantilever beam. In a sense, a very crude approximation, of course. And there is the mass of the propeller plus the unbalanced mass, the thing that's stuck on it, plus 1/3 of the 60 kilogram, and you come out to be 49.69. This is your omega n. Now, the omega, which omega r, in other words, how fast this is turning, is given in terms of RPM, so it has to be corrected. Let me also it's helpful to look at this diagram too. We take a cantilever beam, pretend that the tail section is a cantilever beam. It has a mass. We accounted for the mass, 60 kilogram. And if necessary, we can go and calculate based on the, stuff that we know about the properties of the tail section, aluminum, and then I, the cross-sectional moment of inertia, etc., and the length of it. We can estimate the value of this spring, fancy spring. Okay. But anyway, let's move on. The rotor turns at 1500 RPM in radians per second. Is there. Your R is equal to what we just got divided by 49.69, so 3.16. It's just a matter of going and plugging it in to the mother of all solutions for rotating unbalance. We know everything. We just calculated R. The value of zeta is given to us. We have M. This M is the mass of the rotating component. Okay, the mass of the rotating component. Okay, M naught is your unbalanced mass. Okay, so let's plug it in. It's just a matter of solving for x. Let's see what we have here. M naught is that half a kilogram that we put in there. Eccentricity is 15 centimeter. Right there, we are told that that mass is stuck, that unbalanced mass is stuck to 15 centimeter away from the center of rotation. This is the mass of the block, 20.5. Remember, don't include the mass of the spring in here, because the thing that's going up and down is mass, or that block is, we are not looking at the spring. The spring is outside of that mass. I mean, just look at the diagram here. The spring is out here. The thing that goes up and down is this M. All right. And then everything else you plug in, you get 4 millimeters. This is the answer to part A. Now, part B says, okay, can you tell me what is the maximum value of X? Well, we know when that happens at resonance, right? When R is equal to 1. So, approximately equal to 1, okay? Because remember, look at those diagrams, those peaks are not exactly at the location or equal to 1. We actually went through this thing in the Tuesday's lecture. We found out the location. Actually not Tuesday, but it was, yeah, I think it was, Tuesday's lecture. We found out the location of the peak. And, but anyway, so remember, when R is equal to 1, okay, that means when R is equal to 1, we get the maximum deflection, maximum value of X, the peak. And when R is equal to 1, omega is omega n, right? Omega is omega n. And what is omega n? 49.69. Therefore, the rotation of the rotor is at this speed, omega n, which is 474 RPM. So do not let that tail rotor turn at 474 RPM. Now, if you do, what is the maximum value of X? Let's calculate this thing, this big X, when your R is equal to 1. There we are. When R is equal to 1, this expression simplifies. You get 1 over 2 zeta. And the value of X, just plug it in. You're going to get 18.3 centimeters. It went from 4 millimeter at 1500 RPM to 18.3 centimeter at 474 RPM. Wow, that's a lot of deflection. So if you let the engine, that rotor, turn at 474 RPM for a long time, you're going to have a problem, serious problem. So essentially, to go from 0 to 1500 RPM, for example, you have to pass through this. There's no doubt about it. At some point, it will be 474 RPM. Just make sure it quickly changes the value, goes through it very quickly. Okay? And that takes care of this problem. Okay? Now we're going to do another one. Okay, here is another example taken from Merriam and Craig's Dynamics book. So the situation that we have is we have a machine like that, and it has two counter rotating wheels. Okay, two counter rotating wheels, and there is masses that are attached. Kind of think about it as lump masses that are attached 1 kilogram and 12 millimeters away from the axis of rotation. Okay. Now, these are called eccentric masses, right? These M naughts are called eccentric masses. Okay. Now, the wheels are synchronized so that they go together, they rotate together in counterclockwise, in opposite directions, and they're synchronized so that, you know, like the location of this is exactly the mirror of that. So that's what this thing means. It says the wheels are synchronized so that the vertical position of the unbalanced masses are identical. In other words, this height, and that height is the same. So essentially they kind of synchronize rotating together. Okay. Now, the total mass of this machine is 10 kilogram. Okay. And remember, there's M naught here and there's M naught there. Okay. M naught here and M naught there. And it says find the two possible values of K. There is no damping here. You can see that. We're ignoring damping. It says find the two values of K that basically it says that the force transmitted to the ground is 1500 Newton when they're turning at the speed of 1800 RPM. Okay? So it says, look, the whole machine has a mass of 10. 1 kilogram here, 1 kilogram here. Synchronized so that, you know, basically this is a nice and symmetric problem. Now, find the distance of these masses. These masses is 12 millimeter away from the center of rotation. Okay, find the value of K so that at this speed, the magnitude of the force transmitted to the ground is 1500 newtons. Okay, ignoring damping. Now, the mother of all equation for us for X is this. You might say, you know what? Actually, I remember that there was a formula for Ft, in other words, maximum transmitted force, divided by kind of F naught. Let me go back here. Well, actually, I'm not going to go back. You can go back to slide number, let me see now, slide number, the beginning of the lecture, slide number 5. We had an expression for big X that you can see right in front of you. And we also had the expression for Ft divided by Well, I said divided by F naught, but it's F naught is M naught E omega n squared equal to. I can solve this problem by directly going to that equation and working it out. Or I can get the X, and then if I multiply it by K, because there's no damping, I'm going to get this force. Okay? All right? So that's what I'm going to do. So you find the X, plug in everything that you know. You know E, the eccentricity. You know M naught. Just remember, M naught is two of them. So just remember that there's going to be 2 kilograms here. The mass of the machine you know. The mass of the machine you know, 10 kilograms, right? Eccentricity is 12. 12 millimeter. You have to convert it to meters. And then your R, you have to get the value of R, right? Because we don't know. R is omega, which is 1800 RPM divided by omega n. The problem is that we don't know omega n, okay? Because it involves root of k over m, and we don't know k. So the moral of the story is that, first of all, if there's no damping, this thing simplifies. Zeta is equal to 0, right? Zeta is equal to 0. This whole thing simplifies, okay? And clean it up, big X equal to M naught over M. Omega R, we know what it is. That's 1800 RPM once converted to radians per second. We know M, 10 kilogram. We don't know what K is, okay? All right. Let's do a little bit more clean up here. This is the amplitude. I'm not interested in the amplitude of the displacement. I'm interested in the force. Amplitude of the force, which means that I take this and multiply it by K. Kx, no damping. Kx, okay? The K goes away, you get this. Please notice that slide 5, the expression for Ft was given. You can go there and plug in the value of zeta equal to 0, no damping. You come up with exactly the same expression. Here I found X, multiplied by K, I get the force. Okay? So what do we know here? You're told that this transmitted force, maximum transmitted force, must be 1500 Newton. M naught, there is 2 masses of 1 kilogram involved, right there, 2 times 1 kilogram. There is eccentricity, which is 12 millimeter, 0.012. There is omega R, which was 1800 RPM, but you have to convert it rad per second. And in the denominator, you know omega R, omega n squared. Let me remind you what omega n squared is. Omega n squared is K over M, right? K over M. So this ratio, you can solve for this ratio if you want. You can solve for this ratio, you get 2 values, because it's a quadratic, right? This is a quadratic. This is a quadratic. And you can solve for this thing. This thing, you can solve for it. And you get 2 values. And you can calculate K out of this. Because remember, omega n squared is K over M. Solve it, you get this. Or you, based on this, you solve it, you get that. Okay. And there you are. These are the 2 values of K. Now I do have to make a comment here, and that is, you see that denominator, There are two possibilities. One is this denominator is positive, and that means that omega r is less than omega n. And the other one is that denominator is negative. That means omega r is bigger than omega n. Okay? So keep in mind that when I say solve for this ratio, there is the possibility that one is positive, the other one is negative. You get two roots, okay? So if this denominator is positive, you work it out. If the denominator is negative, you have to put a basically -1 plus omega r squared over omega n squared, okay? In reality, you see that denominator, that 1 minus r squared? This is a bad way of writing it. It should be absolute value of 1 minus r squared. You see that? When you take the square root of 1 minus r squared squared, that is not 1 minus r squared. It is the absolute value of 1 minus r squared. That's why we're getting two solutions. One for the case of positive, the other one for the case of negative. And if it is negative, you have to replace this denominator with a negative of what it is. -1 plus omega r over omega n squared. And you get two values of k. And that is pretty much what this problem is doing. Okay. Now, the next problem that I want to do deals with a turbine problem, a hydraulic turbine problem. And this kind of a structure, this kind of a hydraulic turbine that you see in many hydroelectric plants, dams, it's called the Francis turbine. So it's got passages and flow goes from the top through these passages, and it goes here, pushes on these blades and make the turbine turn. Water comes from the top, goes through these passages, comes down here, and hits these blades, basically make the turbine turn. This is called a Pelton turbine for small scale operations. Okay, so the water comes and it hits these catchers, and they make the turbine turn and the shaft turn, etc. And there is a Kaplan one. This is a Kaplan one. You can see that the scale of this probably, this is a big one. So maybe this whole thing is about 4 or 5 meters high. And yeah, so we want to do a problem which involves a Francis turbine that you can see here. Okay, in this example, I'm going to be using the stuff that we have learned about rotating the balance to solve a problem that pertains to a Francis turbine. So here's a setup. We have a Francis turbine shown here. It consists of a stator. You can see that. This is the stator that stays fixed. This is the rotor, basically, that turns, and the resisting force is coming from the shaft, because this Francis turbine, when the water comes in, it wants to oscillate to the left and to the right, back and forth, and this shaft will prevent that. We are going to assume that the top of the shaft is, we are going to assume that it is clamped. I mean, obviously this is not clamped, but far enough, it's as if it's not moving at all. Now, the water comes in through A, goes through the passages of the turbine, which is right here, and then it goes out through the tail race to the rest of the setup. Now, the rotor, this rotor itself, the thing that vibrates left and right, has 250 kilogram mass, and we are told that this has an unbalance of a certain value. Okay. Now we are told that the unbalance is actually, which is actually m naught E over G, is given to us, and it is 0.005, assuming that's the unbalanced mass. Maybe some of this is heavier, and there's a spot that's heavier, etc. There is eccentricity, and you're told what the eccentricity. You're not told what the eccentricity itself is, but we are told that this product is 0.005, of course, multiplied by G. Okay. Unbalance of this is given to us. Okay. When this is given to us, assuming that this dam is on Earth, then of course sea level, let's say, G is 9.81, and we can find M naught D. That's what we need. Once again, we are told that the unbalance is 0.005 G, or 0.005 times 9.81. Okay. The radial clearance, the radial clearance is 5 millimeter between the stator and the rotor. Okay. All right. And the operating range of the turbine rotational speed is 600 to 6,000 RPM. Now, again, we are assuming that this top is clamped, and what we want to know is the diameter of the shaft. The diameter of the shaft, that we don't know, okay? So that this can operate safely. In other words, the clearance of 5 millimeter is maintained between this. So the maximum clearance of 5 millimeter does not lead to the rotor rubbing on the stator, etc. Okay, and this is overall operating speeds. Well, let's assume that there is no damping. That information is not given to us. So what else can we assume? Let's assume it's not being damped. And we are told that the maximum amplitude of the vibration of this mass due to the unbalance is should be 5 millimeters. Okay. So first of all, how do we calculate that maximum amplitude? Well, we have the formula for big X, which is the amplitude of the vibration due to mass imbalance. Okay. Now, if there is no damping, things simplify. This denominator actually becomes Z is 0. So remember, this square root of 1 minus R squared becomes 1 minus R squared, and the top stays right there. All right. Now, we are told what X should be, 5 millimeter, okay? And this M0 times E, we just got it up here, all right? Let's go ahead. So let me go ahead and write down this 5 millimeter right here. We know that this is 5 millimeter equal to the right-hand side, and notice that we are dealing with the fancy spring. The fancy spring comes from the cantilever beam, and the beam is actually that shaft that's hanging from a vertical position, assuming it's clamped, and then we can calculate the stiffness of it. For a cantilever beam, the transverse vibration is given by this stiffness, 3EI over L cubed. We did this thing maybe 2.5 weeks ago. We are assuming it's made out of steel. Of course, because it's a shaft, the I of the shaft is pi d to the 4 over 64. Please go and check your structural material, deformable bodies book, or stress analysis book. And we're also told that the rotational speed is between 600 and 6,000 RPM, which means a radius per second is given there. And there's the formula that you've got. Okay, maximum amplitude in terms of the right-hand side. So let's find out what the shaft diameter should be depending on the two speeds, the extreme speeds. For example, at the lower end, omega r equal to 20 pi, all right? We know that we are told that the clearance between the stator and the rotor is 5 millimeter, 0.005. This stuff we already had, and we plug it in here because remember, omega R is 20 pi, this top R, remember R is the ratio of omega R over omega N. Here is omega R, you're squaring it because it says R squared, divided by omega N squared, which is omega N squared is root of K over M, but when you square it, it becomes K over M. K, we don't know what K is, but M, we are told the mass of the rotor is 250. I just plug it in here and you solve. You solve for K. Once you have K, you stick it up there, you get the value for diameter. Notice that we got K based on this speed and that clearance, and we got the diameter. Now, we're going to repeat this at the other extreme speed. In other words, 200 pi. So it's just a matter of repeating this, where the speed is, instead of 20 pi, is 200 pi. Plug it in, do a little bit of algebra, you get the diameter 4.01. Now, when you look at these two calculations, probably the first reaction that you have without looking any further into this to say, oh, wait a minute, if that is the case, let's take a bigger diameter, because if we take this, we are safe, right? But it's tempting, but I suggest we take 127 because we're going to check something. Okay. All right, check it out. So look at the smaller diameter, find the amplitude of vibration at the small diameter, okay? You get the K right there, all right? Based on the smaller diameter, this is the K, and of course, the maximum amplitude at 20 pi, this better come out to be, X better come out to be 5 millimeters. And it does, because that's how we got actually the smaller diameter. So this is not surprising. But now let's go ahead and look at the 200 pi. You work it out and you get the maximum deflection of 0.0202 millimeter or 0.02 millimeter. You see, even with a smaller diameter, at the higher speed, we get an acceptable deflection, less than 5 millimeter. So if you insist on taking the larger diameter, fine, but you're wasting your money. Okay. One question that may come to you is, why is this happening? Let me quickly go through a slide here before we do our next example. This slide. Okay. Notice that at higher speeds, the maximum deflection doesn't change that much. Okay, you can see that because this is essentially the maximum deflection normalized. All right, at higher speeds, irrespective of what damping is, that maximum deflection doesn't change that much. So you may want to go and think about this thing. Why did that come out to be the answer that we didn't expect? But that's fine. All right, so let's do our last example. So here's the situation. We have a centrifugal pump which weighs 600 Newton and operates at 1000 RPM. So we have the mass. This is actually the weight, okay, and we have the operating speed. And somehow it's mounted to basically reduce the effect of vibration to isolate. It's mounted on 6 springs, each of them stiffness of 6,000 Newton per meter. Now, look, the thing is that since there are 6 of them, the stiffness that we should take in our calculation should be 6 times 6,000. Now, we have, it says, what is the maximum permissible unbalance to limit the steady state deflection to 5 millimeter peak to peak? In other words, we want big X to be this value, and what we want to know is what is the permissible unbalance. That means M0, remember M0 EG, that's the unbalance, okay? So that this is the deflection, peak-to-peak deflection. Now, we're given 6 possibilities, okay? We're given 6 choices, okay? So first of all, let's write down the expression that we always use for rotating unbalance. It's right here, okay? We just plug in. Now notice that damping value is not given here. Obviously, we're going to assume that damping is 0 because we don't know, we don't have any information about it. Notice that when damping is 0, when the damping is 0, this zeta goes away. Okay, the zeta goes away because zeta is 0. You get this? What we don't know, what we don't know is this M naught times E, okay? And of course, unbalance is M naught times E times G. Yeah, I understand that. We have the operating speed there. This omega is right here, okay? The K is 6 times of that. And you just plug it in and we find out what the value of what the value of M naught E is, because X, what? This, later on, we're going to multiply it by G. Oh, the peak to peak was, we're told peak to peak is 5 millimeter, right? That's what we were told. So peak to peak means 2x, okay? So x itself is half of the 5 millimeters, which is 0.005, okay? 6 times 6,000. We know what R is, right? And omega squared, that's the operating speed, which we can, based on the operating speed was 1000 RPM, okay? Now, R was already calculated here. R was already calculated because we know the weight. There is the weight. We find the mass, 6 times the spring stiffness. We find omega n, and therefore we have R because we have omega. All right. So let's go plug it in. And out of that, we're going to find the unknown M naught times E. Okay. But you multiply it by G and you get 1.4194 Newton meter. Unbalance in the vibration literature is referred to as M naught EG. Okay. Don't give me this. I need one last calculation, multiply by G. Okay, folks, this is the last example that I want to do today. And here's the statement of the problem. We have an air compressor which weighs 1,000 pounds and it operates at 1500 RPM, is to be mounted on a suitable isolation padding footing. And we have several choices. For example, we have helical spring of that this stiffness 45,000 pounds per inch, and we have a shock absorber or a damper basically at the damping ratio of 0.15. And there are several options that you've got. For example, we can use a single spring with no damper, or 2 springs with no damper, or 1 spring and a damper, and 2 of those springs and a damper. And we want to know which one leads to the smallest force that's going to be transmitted through the foundation. Now, first of all, we find the mass of this, weight of it divided by G in imperial units is 32.2 inch per second squared. Sorry, feet per second squared. And then if you want it inch per second squared, that's the units I'm working in, you multiply it by 12. So we divide by 386, roughly that. And this weird unit is called slinch. 1500 RPM translates into this value, radians per second. And let me remind you what the transmitted force was. I mean, going back to the beginning of the lecture, this was the value of the transmitted uh, force. Now, it is possible to rewrite this thing a different way. Notice that R is simply omega over omega n. So if you replace for this R, omega over omega n, leave these things alone, you're going to get an omega squared canceling the top and the bottom, and you're going to come up with this. This is exactly the same thing, except that the R squared is written a different way. That part of it is the same. Now, the first option is right here. In order to find R, we need the natural frequency. So we go ahead and calculate it. One spring, the mass is this. And you go and plug it in that expression. Obviously, R is this. Plug it in this expression and do a little calculation. No damping means that zeta is 0. And you're going to get this value. So it's a constant. This constant, whatever that thing is, M naught E, some value. This compressor has certain unbalance. Of course, unbalance is M naught E times G, but anyway, M naught E times omega squared, because we said that omega squared is going to stick here, and the factor is going to be 2.3866. It's too much to, I just replaced, I was tempted to replace this thing with F naught. I decided not to do that. Okay, so we go here. For the second case, 2 springs, no damper. Do exactly the same calculation. Your natural frequency changes, your R changes. You plug it in here, and you're going to get 3.4423 times that. Third option, 1 single spring and a damper. Just a matter of more numbers to worry about. You get 1.9282 times that constant. And the last option is 2 springs and a damper, and it leads into this. So if you tabulate these, option 1, option 2, option 3, the one which has the smallest coefficient is going to be the desirable one, because that's going to transmit the least amount of force from the compressor into the padding and the ground. Okay? So that takes care of the lecture today. Remember, on Tuesday, I will do kind of a review by going through some problems, and the midterm is on Thursday, and I believe that's June 13th, during the lecture hour, okay? During the lecture hour on Thursday, June 13th, and it's going to cover through the material, through today's material, okay? And good luck.